right, if you guys are accustomed to converting between decibels in linear forms, that means twice the distance would be 6 dB, would give you that type of a problem. Anyway, so as you go in distance, the signal is degrading, getting smaller and smaller and smaller. So he gets the signal over there, and depending on how far away he is, he's able to see it at a certain amplitude. And so depending on where his ability is to hear, how good it is to hear, some receivers might be able to make it out, because it's a small signal. Some receivers won't be able to make it out. That's sensitivity. So someone's sensitivity might be that I can hear maybe a signal that's at minus 115 dBm, maybe. Well, another sensitivity, or another receiver, might be only capable of hearing minus 112 dBm. It's just 3. It looks like 3. Looks like 3. 3 dB is sure, but not 3 dB. But when you think about 3 dB, what is 3 dB? 3 dB is half. Yeah, so if you do 10 times the log of 1/2, what does it give you in your calculators? It gives you minus 3, right? So minus 3 means you just lost half your power. So in linear terms, volume-wise, if you're putting it on a scope and you saw the amplitude, it would be half the signal. It would be half of that signal. So it's 3 dB are not something to sneeze at. It's the difference between being able to hear something and not. So let's get an idea for what 6 dB is all about. If someone had a difference in their sensitivity to hear by 6 dB, that means that that person, the one who has 6 dB better sensitivity, can hear when he is twice as far as the first guy. So if Sam can only hear, Sam can hear from across the street when I yell, and that's the best. If he moves 1 foot back, he won't be able to hear me. But if someone has twice as good a hearing, 6 dB better sensitivity than Hussam, then he can go twice as far and he can still hear me. And it's exactly the same concept here in receivers. So you started with your antenna, you brought the signal from the RF, you brought it to baseband, and now you converted it back to the original form, which is spoken word. You put it in your speaker. That's the real simple transmission and reception of these signals. I'd like to stop there to give you guys a chance to ask some questions before we move to the next part. Anybody have any questions?
Sensitivity.
Yes.
The techniques to go and increase the sensitivity of a receiver. Today, what's the techniques?
Okay.
Yes.
Yes.
It's hot. Stuff said it was good. For a couple, give you a ticket.
Alhamdulillah, you're not a cop. Huh?
Haram is the way he's taking his space and somebody else will park.
Oh, لا يا زلمة، ما صفيت عن
لا لا بس
السمرة الألفت
بس ما is it's okay.
they're gonna blame me, huh?
He's a
Okay, وريك على الإكزام بعد. Yes.
So you're not the only one who sent in a signal at a certain frequency. That's why the directive antenna is what only grabs this signal.
Yeah. So the antenna, if that's the only frequency being used, it can be a very, very simple receiver, exactly the way we talked about it. If he's the only one in the area used, it's a very good question. And it adds into Hussam's question. If I am the only one in that area using that frequency, I have that antenna, my system is as simple as take the RF. All I need is to convert it down back in frequency using a mixer and a local oscillator. If you guys took these classes, you take your RF and you mix it with a different signal, either much higher or much lower, to get you back so that if you did that frequency, the RF frequency minus this other frequency, it gets you back to your baseband signal, the one that we're looking for that's less than 100 kilohertz. Or you take something much higher and then you subtract this one from that one. But now you have a whole bunch of other frequencies, because what mixers do, they take this frequency minus that one, 2 times this frequency minus that one, 1 times this frequency minus 2 of those. So you have to filter out those other guys to make sure you don't hear images of that same signal. So you bring it back. And it's so simple if there's nobody else there. But if you start having more than one frequency, then more than one person speaking on that frequency, and it's within your own system, that's when you got to start being clever. Like we talked about, by choosing antennas that are selective and moving, to point to the guy who's speaking, or you decide to become a coordinator. You fix things in software. You decide, عالدور كل واحد يرفع ايده لما يرفع ايده بشوفه وبخليه يحكي. That way nobody interferes with anybody else. But if it's coming from an outside of the system, that's a totally different problem, different way to solve things. And going back to the directive antenna, just looking at the guy you want to talk to blocks everybody else out and gives the most gain to the one. So what it does, going back to Hassam's question, where does sensitivity come from? So when you look at a receiver in its most fundamental perfect form, where does everything has a lower limit? The lowest limit of what's the lowest signal, as Akara was saying a few minutes ago. What's the lowest signal that I can detect and know what that signal was? Where does that come from? It comes from physics. So in electronics, do you guys remember the Boltzmann constant, KTV? Do you guys remember KTV from chemistry, physics?
25 nanovolts?
No, well, it gets you to a really, really small voltage, but it's even much smaller than that. So if you remember KTV, the Boltzmann constant, it's a really super small number. I don't remember what exactly it is. I can't regurgitate it, but I can tell you the equation. KTV stands for, if you were to multiply K times T times B, K is that Boltzmann constant. It's a fixed constant. T is the temperature that you're functioning at in a particular resistor. And if you go inside of a resistor in the electronics, and you look at the temperature in Kelvin, and you use your bandwidth of your signal, how wide is your signal? We didn't even talk about the width of signals yet. But if you had a signal that was 1 megahertz wide, the information was contained in a signal that was a full megahertz. You guys in the labs are only used to looking at spikes probably in signals. You're looking at a signal that looks very, very narrow. Maybe you haven't even considered how wide a signal is. But if you took a signal that was only 1 hertz wide, your information was contained in a signal produced to just 1 hertz. Then your sensitivity, if you're looking at signals that are only 1 hertz, is minus 174 dBm. Yeah, you can hear so many things at minus 174 dBm. But already, what's the problem with those types of frequencies going down that low? We said something that was 100 kilohertz. If you wanted to transmit 100 kilohertz, then you become susceptible to the antennas that are unreasonably long. So as you increase your bandwidth from your 1 hertz signal, you're increasing it, increasing it, increasing it, increasing it. The KTB, instead of being multiplied by 1, the K and the T, when it's 1 hertz, gives you minus 174. But as you increase the bandwidth, you're letting in more noise. You're letting in more noise. Because now all of those electrons inside those resistors are all vibrating and creating noise based on the temperature. As you turn the temperature up, something heats up, those electrons start moving faster. And they start creating more noise. Crank the temperature up, more noise. So the numbers I was quoting, the minus 174 dBm in a 1 hertz bandwidth, that's at room temperature. It doesn't change much as you go for our types of temperatures, like up to 80 degrees C or down to minus 40 degrees C. Very little change in that type of sensitivity number. We'll talk about more of the components later. So if you start at 1 megahertz, a 1 megahertz bandwidth signal, then you would have to, when you multiply by the 1 megahertz, so now you're taking, what's 10 times log of 1 e to the 6th? 60, right? So if you had a 1 megahertz signal, instead of being at minus 174 dBm, your noise floor, suddenly it goes to minus 60 of that, you would go to minus 114, right? Minus 114 if you had a 1 megahertz signal. So let's get an appreciation for what that means. It means that if everybody in the room, what noise floor means, because that's what this is creating. It's creating a noise floor. What's the lowest? What is the level of the noise? That means that if everybody in this room was talking at the same time, there's suddenly, if I want someone to hear me, I have to talk above that. I have to talk above the level, the average level of the people who are speaking in the room. People are buzzing. Do you ever go to a restaurant and, sometimes it's just a buzz. When Kutra Nas, or you go to a big conference hall or something, people are buzzing. It starts to sound like a buzz because there's so many people talking. And then suddenly you hear something, and you hear it when someone just speaks really loudly. Or something goes over the speaker system, or someone next to you just starts talking really loud, or someone comes real close to you, and then you can hear it. But you can't hear your friend who is in the middle of the crowd talking to someone else. You just can't hear him because now there's this higher level. But if you left that room, you can hear someone and decide and hear what they're saying who was speaking at the same level as when he was in that room. Now you guys are alone. The buzz is gone. The buzz is gone. And so now you and that guy who are talking, you can speak at a much lower voice. And you can hear each other because the buzz is gone. What happened in that room is that you raised the bar to say, what's the lowest level of voice that I could use in order to understand? Because somebody raised the noise floor. Somebody made the noise in the room so high by doing all this buzzing that I have to speak higher than it in order to be heard. So if we look at them in terms of delta, a delta, so this is my noise floor, someone's speaking, everybody's speaking in the room. I have to be able to speak, depending on the sensitivity of my receiver, I have to speak so many dB above that noise floor. I have to be 10 dB, I have to be 6 dB, I have to be 100 dB, I have to be whatever. We'll talk about where those numbers come from, but the original part of this is the noise floor. It's created from something. It's created, yes?
So, when we go back to the buzz.
Mm-hmm.
So a guy like Ali, for instance, young, has certain interests. We walk in and suddenly he can detect female, male. He can detect female,
Okay.
different ages, for instance, and suddenly he homes in on somebody in his age bracket.
Mm-hmm.
What is that called?
Let's call this on what Joe was. I don't know. So that's a very complicated technique. So let's say you brought the information in. The buzz is there, like Sam was saying. The buzz mawjood, right? We said one way to do it physically is to have antennas that, you know, like you ever see these guys, these Secret Service kits. Like if you want to hear somebody and they're talking over there and they're in a crowd, if you had the way to just point a laser at this guy and just point it at his mouth so you can see so you can carry the vibrations that are coming out of his mouth and carry them back to you, the narrower you can make your beam so you can block everybody else out. And you're not really blocking them. All you're doing is you're focusing on him. But the end result is people call it you're blocking everybody else out. So you can focus on him. That's the physical way, but that's not what Hassan was asking about. That's the physical way of doing it. So some people, there's these very, very advanced techniques that people apply, and this is not my area of expertise, but what people do also is to improve their sensitivities, there's advanced techniques of how to separate signals out. So you can take that, the information comes in from your antenna, it's in the RF, and it goes to the baseband. There's techniques you can apply in the baseband. If there are multiple signals in there, how do I separate those two signals out? You have to have ways of how do I know which signal do I want? How do I know which voice I want? Is there something detectable in Ali's voice that I can use and say, every time I see this pattern, that must mean it's Ali's voice, I'll pull it out. If it's a competition between just 2 or 3 or 4 voices. But if the problem is noise, general noise that's all over the place, and it's not a specific interferer that you are trying to separate, am I listening to him or am I listening to her? Who am I listening to? If it's just too simpler to select one versus the other. But if the problem is a physics problem, and I made the analogy of the buzzing room to say that if it was equal and flat, then you could not decipher one voice from the other if you were below this threshold, because that's kind of what we call in physics white noise, like Gaussian noise. Gaussian means like it's completely random. There's nothing you can do about it. It's underneath the noise floor. No one can detect something below minus 174 dBm and a 1 hertz bandwidth. That's just physics. The electrons are vibrating and they're creating noise at minus 174 dBm. So unless we know how to synchronize and know what rate and see the rate that they're vibrating at, there's no way to synchronize to the noise, because and by definition, and maybe this is something in advanced research that people will eventually discover, who knows, that there is a pattern to the noise. But as long as we can't see the pattern of the vibrations in the noise at minus 174, it will be a totally random process, and you cannot synchronize to it. Then anything that goes below it, you can't decipher it from it. So the sensitivity originally comes from that, but we degrade sensitivity. So not every receiver, so let's go back to the analogy of the band. We said 1 megahertz signal is at minus 114. 10 megahertz signal is at minus 104 dBm. So that's if I had a perfect receiver, if my hearing was not distorted, it's 100% perfect, I could hear at minus 104. Let's just take that as an example. But what happens is, okay, minus 104 is still pretty low, so I need some circuitry in the front to bring it up a little bit, to bring that signal up. So someone said, okay, we'll just put an amplifier in front of it, and you can go as low as you want. But has signal, put an amplifier in front of it. When it comes in at a low level, put a big, huge amplifier, bring the level of that signal way up as high as you want it to go. Let's say I want it, I can put in a 50 dB signal, bring that signal up 50 dB. But as you're bringing the level of the signal up, of course, amplifiers can be expensive. It all depends on the application that you have. Cost has to be taken into account before you design something. If you're the government, cost is no option behind it. You spend as much as you want on whatever you want. But for commercial type of applications, $1 means something. We were talking to Hassan, we're designing some radios for these outdoor wireless environments. In the past, for the base stations that we all worked on, we didn't care, no one really cared about cost. Oh, you're going to add $10 to the base station? Oh, wonderful. Oh, put it in there. We had switches that we were adding at $25 a pop that no one really scrutinizes $25 in a base station that costs $25,000 or $50,000. No one really cares. But when you're selling a device that you're trying to sell it for $100, a quarter means something. $1 means a lot, and you have to get scrutinized for that dollar. So adding a lot of amplification in something is costly.
Add to it actually also the logistics of where to install it and all that stuff.
Yeah, so the size,
issues.
all of these things matter. Like I said, size of what you're going to put on the tower, how much power it draws. You're limited by so many things when you come to install. These guys are experts in deploying these networks. So when you say, I'm going to install this base station on this guy's tower because, okay, he has to transmit it for me. Someone has to put up a transmitter on this tower somewhere so that they can hear me. And the reason why we don't just put it at the ground here, right, so we can put our transmitter here on the street, right, and just say I want to send the signal to Hassan's house from here. But the problem is when it's this low, it's going to meet 50,000 houses, cars that are moving, trucks that are moving, trees that are in the way, people walking. There's so many obstacles, so you got to go up on a tower. And all the cell phone towers are on tower. They're towers for that reason, because you want to create as much of what we call, we're going to get to this in the later part, line of sight type of communications. You want people to be somewhere where you're closest to the tower. This is like saying someone who's outside of this house, outside of this building, and someone who's inside. Yeah, someone who puts their ear real close to the window, maybe they can hear what we're saying. Or if we yell to the guy outside, depending on how good the windows are, they might be able to hear us. But only if they had really good sensitivity, only if there's no other noise in the room. You got to quiet things down. Hey, everybody keep quiet, I want to hear what the guy is saying. All those types of things come into play. So deciphering and picking signals out, as Sam was saying, if there's a signature, there's something that I can pick out, either with my signal, of what makes my signal distinguishable from his signal, or what makes his signal distinguishable from mine. Is there a pattern in his signal? Then in signal processing, in DSP, digital signal processing, which is a very important field, you can play tricks inside of your DSP to figure that out. Right? So back to the bandwidth story. Right? So the bigger the bandwidth of your signal that you're sending, meaning how wide is my signal. So I might say I'm going to send a signal that's centered on 1 gigahertz. It's a 1 gigahertz signal. It doesn't say the bandwidth, it says what's the center frequency of the signal that I'm sending. So at 1 gigahertz I'm sending from my antenna. But the signal might be 1 megahertz wide, the information is contained in a 1 megahertz wide signal, or it might be in a 10 megahertz wide signal, or it might be in a 20 megahertz wide signal. So the wider the signal, the more noise you introduce, because the total noise power coming into your channel is increasing. That noise floor keeps coming up. The wider your signal, the higher your noise. So the wider your signal, your sensitivity is not going to be as good on the other side because you just raised your noise floor. By default, you raised your noise floor from the signal that you sent up, that you sent over. By the time it gets to the receiver's floor that he sees on the other side is higher. He needs signals above now a higher noise floor, so his sensitivity got worse. If you gave him a narrower signal, now his floor goes down and he can hear signals lower. So let's say before, with a wide signal, let's say a signal started at 1 megahertz and then you increased it to 6 megahertz, right? Or if you increased it not more than 6 megahertz, you increased it to from 1 megahertz. Let's say you increased it to 10 megahertz or something like 10 megahertz. We said the 10 meg, from 1 meg to 10 meg would drop you 10 dB. So drop it something to give you 6 dB. I'm going to go to that 6 dB number because it's very magical, that 6 dB number, is because it refers to twice the distance. Right? Because we said the relationship between distance and frequency and loss, propagation loss, is directly proportional to lambda, wavelength, over r squared. So distance, every time you do distance, you have to do 20 times the log of the distance, which is essentially, if you double the distance, it's like 6 dB, right? So if somebody has a 1 megahertz signal, or someone has something like a 10 megahertz signal, the person who has the 1 megahertz signal might be able to hear me at, say, 6 miles, and that's his sensitivity, if it's line of sight. So let's say he can hear at 6 miles. The guy who is at 10 megahertz can only hear me at 3 miles. And so as the frequency goes up, the bandwidths, as the bandwidths are going up, the sensitivity is also going down. You're not able to hear signals that are as good. So sensitivity is degrading by default. Any questions on what we said so far before we start another phase? Everybody understands transmitter from its core, what it is, without talking about modulation. We haven't talked about modulating except a little bit in its raw form. You have the systems, the pieces that are in a communication system. You have the generator of the information, which sometimes is considered outside of it, but these days it's moving in. You have the communication system that consists of the data comes in, it has to get coded, it has to get converted to digital signals, zeros, ones, phases, frequencies, and that's the modulation piece. You have to dig in a lot more into that one. And then you change the frequency of it to make it something that's reasonable to be transmitted at those higher frequencies. Otherwise, the bandwidths become too big, the wavelengths become too big, and the antennas become huge. So you convert it to a reasonable frequency. You amplify it, you get it ready, you send it out, you put it on you connect it to an antenna that resonates at the frequency you want. It gets sent over the air. It degrades in power with respect to f over lambda, proportional to that. Gets to the other side, the other antenna picks it up and converts it, takes the RF, converts it back to the baseband signal, and deals with your data. That's the general communication system in a nutshell, the high-level overview of what happens in a communication system. Any questions about any of those pieces? You have the antenna, the transmitter, and the receiver, and another transmitter.
Yeah, that was typical in the past of a communication system over RF, but now we're seeing multiple different systems, collecting, transmitting, and of course recomposing and presenting the data. So have you seen things like, for instance, going from RF to optical to RF, back to digital, and so using multiple systems based on how you want to transmit and get to a certain point.
And so Hassan's talking about there are multiple sources. There's multiple reasons why you want to send something over a wireless interface. All of these things, the word interface, you got to get used to hearing the word interface. Okay? An interface is if you're looking at a radio system, a transmitter, or like your computer. Let's take your computer for an example. Look at all the interfaces that your computer has today. Right? You have, if you plug it into an Ethernet port, an Ethernet cable, so you can get network connectivity. We call that's the the wired interface, because you're connected it to the Ethernet wired interface. So that's one interface between the world and your computer, right? Interface meaning like the boundaries where things kind of come together from two different places. And then we have the wireless interface. In our computer, how many different wireless interfaces do you guys think we have on a typical computer these days, right? Who has,
I think they come standard, they come Wi-Fi, but obviously you could plug in and have, you know.
yeah, so I mean, even just standard, you got, like you said, the Wi-Fi, and you have Bluetooth,
Bluetooth.
right? That's also a wireless interface, communicating, maybe also kind of adding on to what Hassan was asking about, and the brother was saying some even more advanced things too, is that you can add other interfaces, but your computer comes with a Wi-Fi interface, so you can transmit to things in the Wi-Fi domain. And then you have another wireless interface called Bluetooth. If you go to your phone, you've got
Infrared.
Wi-Fi, and you got infrared. Forgot about infrared. You know, that's a wireless interface between your computer and some other transmitter receiver on the other side. Your phone has got also GPS. Yes, it's only on the receive side. The GPS doesn't transmit anything from our phones. At least we don't think they do, right? You've got those types of interfaces, right? And all of these are taking information that's coming from somewhere, either generated by the user of that device, the phone itself, or taking it from that wired interface that's being sent from someone else unrequested, taking that information in and doing something with it. So whether you have a fiber interface, a fiber is another type of wired interface. So the Ethernet we talked about is the one that we connect directly to the computer. There's another interface that Hassan is very familiar with. Barakallah feek.
I don't know if it's working.
One of these non-bands, which is what
See
I
if
just
you put an off on.
through all these interfaces, they could have tried and kept the same interface. Why is it that we don't try to do everything over Wi-Fi? Why do we have Bluetooth? Should we not have Bluetooth?
Speed.
I mean,
Transfer rates are faster depending on what you use.
well, the Bluetooth is at a different frequency. It's at a fixed frequency, right? And Bluetooth is meant for short-range communication. It can be higher speed, it can be a lot lower speed, but it's meant for really short communication links. But Wi-Fi was also meant for shorter communication links in your home, and they say if you were line of sight, you can get the best throughput rates if you were not more than 300 feet away from the AP in your house. But everybody knows that if you put your AP somewhere like in the basement, your wireless router, everybody has a wireless router at home, I think. And if you go to your room upstairs, somebody's trying to use the internet up there, and then someone's using it downstairs. A classic example, I'll give you an example of what happens in my house. So our wireless router is in our family room, and somebody will be downstairs close to that router and having a good time. Speeds them, doing whatever they want, and no problems. The videos are clean, they're watching the Vines, all these nice jokes, Soya with videos, no problem. Somebody goes upstairs, and they start using the internet upstairs. Suddenly, Yaba! What happened? The internet battal yishtal. And they're not even using heavy bandwidth. So in Wi-Fi, so remember how we were talking about taking turns and somebody has to be the master. So Wi-Fi, it has this protocol. This is what, so outside of the RF, so in communication systems, in any electrical system, there's always a struggle between the hardware guys and the software guys. The hardware guys, we make the antennas, we make the receivers, we make the transmitters, and then the software guys say we always have to come in and clean up after you guys. We try to fix things in software because it's cheaper to fix something in software. So that's where the raising the hand thing comes up. In Wi-Fi, they said, here's what the protocol, and another term you should get used to is protocol, which is the agreement for how we will communicate. So GSM that's used for cellular telephone communications, it has a protocol of how you establish a call. When you want to establish a call with the tower from your phone, there's a protocol for how to establish it. There's a protocol for how It hands over, if you're driving your car and you move from one tower to another, there's a protocol for how to hand it over and when to hand it over, and all the signals that have to pass between the towers, between the stations, between the subscriber and the tower. All that information is handled. So that's the GSM protocol. This is the Wi-Fi 802.11a or B or G or N and AC and AD coming up. Those are all protocols. So this 802.11 protocol, it says that the way we will agree to communicate between us, if all of us are in the network trying to talk and send data through the AP, we're all equal. Even the AP is considered like the AP is the access point. So all of us, let's say I was the access point, and I'm the one who has an Ethernet interface behind me that connects everybody to the world. The way that your signal at your home from your Wi-Fi device or your laptop, you're in your home, you're trying to do some browsing, you're trying to send emails or whatever, it has to come through me. I am the access point that gives you access to the network because I have fiber behind me or I have a cable behind me that connects me to the internet. Maybe we can have Sam give us a real nice overview of what is the internet and where are these nodes, where are these servers in the world. But since I am the access point, you have to come through me. But what Wi-Fi said is that, okay, everybody's equal. I'm going to make this real simple. Whoever wants to talk, just listen first. If you hear nobody talking for so many seconds, go ahead and talk for so many microseconds. So it works out real nicely if there's not a lot of people there. And it works out real nicely if everybody in the room can also hear everyone else. If you can only hear me and you can't tell when someone else is talking, how would you know that there's no one talking? You have to be able to hear them. In order to know that no one else is talking, I can go ahead and talk. That's the Wi-Fi protocol. Even the AP has to listen before talk. That's the listen before talk part of the protocol. So he's listening also to see, is no one else talking? Because هذاك طلب مني معلومات, I have to send it to him. He asked me for bandwidth. He asked me for some information to send it out. So I'm waiting for him to send it. He sends it. Go ahead and send. Now I was waiting for someone else. I had to send him information. He's waiting because it came in from the Ethernet. Thought of information for his web page. A few minutes ago he was downloading Yahoo to try to open up his email. He requested it. And so now it's waiting. The information came back, but somebody else over here took the air interface and said, okay, everybody else is waiting. So he sends it. Now it's your turn. I'll send it to you. Now somebody else is listening. It's quiet. Two other people wanted to talk. They send at the same time because they both thought the medium, the protocol was available. They both send at the same time. A collision happens. The data arrives at the same time. Both data is lost from both of these guys. Then we agree, okay, there's a protocol. So someone said, okay, this is bad. So we'll have an agreement. If there is a collision, then we're going to have what's called a back-off. We'll have a clever algorithm, might be very simple in the beginning. Okay, if there is a collision, if you have no confirmation from me that I got your data, send it again at a random number. Everyone pick a random number, and you send 30 microseconds later. You try again and listen. 100 microseconds later, if it's available, send it then. If not, you got to wait your turn and resend it another time. So what's happening in my house is that when someone's downstairs, they're very close to the access point, to the wireless router. When someone is upstairs, suddenly, because the devices don't transmit as much power when they're talking to the AP, I am down at the AP or whoever's down at the living room, the power transmitted from that laptop or from the device is very low power. And so they don't need to transmit very much power. So the person upstairs can't hear me. They can't hear the person down here. So now there's collisions all the time. Both people don't get their information sent through. It's not about sensitivity, because if the person downstairs stopped working, then the person upstairs would be doing fine. It's a matter of coordination. They're both trying to send at the same time. So this time it is the software people's fault, Hassan, not the hardware people.
Probably got an old one, right?
No, it's not old. It's new. So there's multiple ways to solve these problems. You can decide to make a fancy coordination system. You can decide to make a fancy receiver system that decides to be selective when they decide to hear somebody or hear someone else instead. They can do something like that. So these protocols are all varied. Hold on.
Well, they have two frequencies now, so upstairs 2.4, downstairs 5.
Oh, yeah, so there's so that was a hardware solution, by the
Yeah.
way. I'm biased towards the hardware because I came from hardware. Sam is a computer science guy. I think he can solve all of our problems. The system that Sam is mentioning is these days the 802.11 protocols, the A, B, G, N, the AC, and the AD, and what comes after that. They're starting to build chips. The whole system is on a chip. All these receivers now and the transmitters, they're residing in an individual chip, a single chip. Zaman, just to digress one more time, the base stations that we used to build for Hassan were they were as tall as the ceiling, and it was this wide, and it was this deep. Just to send voice signals, just to manage people's phone calls. But as time changed, so we had a separate, if you can imagine, just to talk circuits for a little bit, you would have a whole separate board that was this big with its own housing to manage the temperature, to make sure the thing doesn't get too hot, because every component is rated for a certain temperature that you put in your circuit. So you have your amplifiers, you have your transistors, you have your power supplies, you have your filters, your mixers, and all those. So on this one amplifier board, you have its own power supply, its own fans, everything to keep everything cool. So for every X number of users, you have to have one of these boxes. One power amplifier box, you have to have one transceiver box, you have to have one digital controller box, you have to have a fan box, you have to have until this thing became huge. And that was because all the components were individual. A lot of times, so the stuff that you're studying now, circuit-wise, most people will never use anymore, unfortunately, because all of that is now built into a lot of these chips. And so regular circuit design has kind of gone away for the most part. So if you want to do circuit design, you must decide to go into IC development. If you really love circuits, you must design ICs. You must go into the IC design area. So you need to do something like VLSI and FPGAs and designing ICs, integrated circuits, designing application-specific ICs, ASICs. If that's what your passion is, circuits, you got to go into that type of development. So what's happened is these power amplifiers, these mixers, these synthesizers that change frequency from taking me from my 100 kilohertz, taking me to my 1 gigahertz, it's all moving into these chips. And the faster these chips get, you can start sampling at a much higher frequency. So maybe I can sample a 1 gigahertz signal where I no longer have to convert it. I can sample at 1 gig, so now I don't have to have a conversion to bring it back down to 100 kilohertz. No, I can sample the 1 gig and get a kilohertz from it. I don't have to convert it back down to 100 kilohertz. I can just sample it and get the 100 kilohertz out of it. So as these more components move into the chips, everything gets smaller. So now the base station that used to be that big, when I left that team about 12 years ago, the base station was like this, the GSM base station. It became so much smaller. So every few years, more stuff gets integrated in, but they will never, ever be able to get rid of our antennas, never. Because if you want to transmit something at some frequency, you have to have an interface between you and the air. You have to have a way to transmit it over the air. Yes, the PAs will go into those chips. Yes, the LOs and the mixers and everything will go into that chip, and maybe someone will argue you'll have a chip and an antenna. And that's your whole transmit and receive system, because everything is moving in, all the amplifiers and everything, so it looks like a chip. But only the people who understand circuits, only people who understand the communication system can work to design those chips, because somebody has to design them. It's the same thing, but now they're all in these ICs. You don't need 10 engineers to design a base station hardware piece anymore. You just need to buy your chip and 2 really smart engineers who understand the guts of these chips to integrate it and get your antenna and understand the sensitivity of the transmit power and the noise and everything else.
I think probably we're got 17 minutes left. Do you want to finish up, or maybe we try to schedule another time for where we go into a much deeper?
Yeah, we should probably agree on an agenda
Yeah.
for what specifics to go into, what people are really interested in knowing more about.
Yeah.
I mean, a lot of these concepts can get very, very detailed. So, for example, like if we, so as we said, the subsystems are interfaces. You have your antenna, you have your transmitter, you have your receiver at the highest level of the blocks. And in each one of those, in the transmitter, lumped into the transmitter, there's so many pieces. Like you've got things that we didn't even cover yet. Like what do you do about security on both sides? What do you do with that? Something that Sam can probably speak to a lot more than I can on the interface side. But each of those blocks we can go into different levels of detail. We already said I think nobody's really interested in the circuit side, right? But maybe we can talk about the antennas a little bit more without going into too much detail. But to look at an antenna pattern, to say, let's say someone asked you, and maybe this is where I want to ask a question, is like, we should probably make this centric to people who want to understand the communication system and how to deploy it, as opposed to the guts of circuits, the guts of algorithms, unless they particularly obtain to a deployment, right? Should we focus things more on deployment?
I think probably what we probably want to go in, just so we can talk about why we have, I mean, it's good to have a very informative, and this man, alhamdulillah, he's an expert in this, and he's been almost only 5 years. We don't want to tell you your real age.
Yeah.
So he's gotten all his knowledge in the last 5 years, inshallah. He's a young man. But in the history of communications, and alhamdulillah, he's gotten an opportunity to be a designer. He's gotten an opportunity to become he's managing now the virus he's been putting out for the last 20 years. So he gets to see actually.
It's getting released Monday, by
Yeah.
Monday morning at 7.
So
You're free at last.
So the opportunity is that sometimes as when we come out of school, we have this vision of the world, and that it's really on paper. It might be in a computer, and very much like we're going to go in and start designing ICs, or we're designing software, and that. So we tend to sometimes go into the field in different fields. When we work 10, 20 years, like many of us, and we have no idea how our products are deployed and how they're used. And so today, I think we've been talking about, today, one of the reasons we're having this class, we think this is a foundation of what's coming and what's currently being deployed as we speak right now. And we're talking about machine-to-machine communications, and this is where, plays into the architecture, the foundation of what we're talking about. We used to talk about a few, if you remember a few years ago, the way you sold the cell phone is your wife was going to break down somewhere in a dark street. You really need to have this huge phone in there to call for help. And today, only 10 years later, I mean, our children are using it, for all sorts of things, as well as us for communication and business and that. So that device now is a library, now it's communication, it's entertainment. So it's become almost representing our entire world. And so we're beginning to even see devices that are minuscule, very small devices being now deployed on poles, being deployed on, for instance, generators, all sorts of inventories, just transmitting, saying, I'm here, this is what I'm all about, I'm okay, I'm not okay. So billions and billions of devices. And so what Basman was talking about is that we used to have maybe a few people talking about, like you walk into a restaurant and maybe there was 15, 20 customers. Now there could be hundreds or thousands of customers. So that white noise is becoming more and more prominent. And so if we don't understand, for instance, how to recognize it, and we don't have a background in it, then you're like Maskin Ali, who's going to California and he's beginning to see it in real life as like all of these devices talking, and they're dropping out and they're not working because the people in the background really, all they were concerned about was just deploying a product, selling a product, but have no idea how it will fit into a network. And so for us, I think this is a foundation, and we want to talk about going from a foundation to actually understanding deployment, and then from deployment to actually understanding how it's being applied today. One of the things is that there's a company called Silver Springs Networks, which just signed a huge contract with ComEd to do what they call smart grid technology. All that is now every house has a meter, electric meter. Remember in the old days, the guy used to come, read your electric meter. If you had a dog, he wouldn't come to your house. He'd just tack on your bill and you got a huge electric bill. Now, that meter is gonna start talking, and it's gonna talk to something. So that transmitter that this man was talking about, it has to talk. But the problem is there's no towers for that meter. So what they're making them do is talk to each other. So it's exactly what this man is talking about. Is like, you hear me, I'll talk to you, Shadi, and Shadi will talk to this man will talk to Ali, and so on and so on. Problem is, like you said, not all of our ears are the same. Not all the products are not going to be the same. They're probably made from different manufacturers. So we're going to have thousands, billions of devices maybe in the next few years having all sorts of issues. Much of the issues that we see today, we see in the past with telephones. And many of these people that are deploying these don't have an RF background. We've sat with them. They don't. They have no idea how, but yet they've deployed 16.5 million devices. So they're doing something right, and they're moving it in that direction. So if you're talking about where the future is, this is where the future is. These devices, small, they're not transmitting at high power, and they're talking to each other and relaying information.
So I heard at least a couple things from Sam that we're interested in maybe understanding the different protocols. You talked a little bit more about identify the Wi-Fi, identify the mesh, identify point-to-point, point-to-multipoint, and talk about them as protocols, high-level protocol, what the protocol does. And then talk about things that deployment teams worry about. And then if anybody's interested in product development, if someone wants to develop a product, what is the development product cycle, life cycle for how you start developing and what it takes to develop a product. Those are at least some of the things that I heard. Maybe we can prioritize them offline, how you guys want to approach those next time, inshallah.
Yeah, I think one of the things also that they used to say the best architect was the person who started out as a carpenter. Because when he was a carpenter, he used to swear up and down what a bad design. So when he became an architect, he'd go back and say, well, you know what? The bathroom should all really be on top of each other, for instance. One stack. Not where the husband and wife decide to put them because it's a mess and it'll never work. You know. For instance, maybe the roofs should be a certain way because in the long run, they're going to be maintenance proof. And so that's, I think if you're going to go into an area where you want to be a designer, this is a great place to actually come in and actually see the mistakes people do. And that's when you go back, like Basman, alhamdulillah, and then he said, you know, I used to sit and theorize on how I want to do this antenna and could be 1,000 meters or 100 meters in that, and the poor chump that has to go up there at 100 feet up in the air and he's struggling with it.
That's his job.
You know, and he's trying to figure out how to align it in that, and it's going back and forth. So this man got a lot of that knowledge, you know, based on mistakes. And we don't. Why should we continue to make the same mistakes over and over again? You know, learn from the people who have already done it. I think it'll just make people like yourselves who are just getting ready to graduate, alhamdulillah, you know, you'll be that much farther ahead. And then there's also opportunities, of course, with these new technology rolling out. As all of us, we want careers and long-term careers in the right path. There's an opportunity to go into these kinds of careers. Yeah. So yeah, I mean, I think the foundation is very important. Understanding the technology is also important, and then understanding the application also. And alhamdulillah, I think we have we have young people, we have people with a lot of experience. I think, you know, we'll put together some very nice classes, inshallah, in the next few weeks.
So Liz, sorry, I apologize if I went to the wrong detail today. I wasn't.
No. Actually, the foundation.
Clear on what,
the foundation is very important.
So let's just solidify which pieces we want to talk about next time, inshallah, and then we'll approach it from that perspective in terms of which one should come first.
I think to be honest with you, for us it's. I mean, I like the horse, and I like the rider, and I want to keep it. To be honest with you, the reason I do that, yeah, it's you know why? Because it really we haven't gone really.